Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today. Construct the lexicographically largest valid sequence, Leetcode 1718. If you are new to the channel, consider subscribing. I try to make daily videos on the problems related to data structures and algorithm, including detailed explanations, optimized solutions, and step-by-step walkthroughs to help you improve your coding skills. Now to the problem. In this problem, we are given an integer n and we have to find a sequence that satisfies all of the following conditions. The integer 1 occurs only once in the sequence. Each integer between 2 and n occurs twice in the sequence. And for every integer I between 2 and n, the distance between the two occurrences of I is exactly I. And among all the valid sequences that meet these criteria, we must return the lexicographically largest sequence. Now to the definitions. The distance between the two numbers on the sequence ai and aj is defined as the absolute difference of their indices I and j. And a sequence A is said to be lexicographically larger than another sequence B of the same length if at the first index where they differ, ai is greater than bi. For example, the sequence 0190 is larger than 0156 because at the index 2 where they differ, 9 is greater than 5. And the problem guarantees that a valid sequence satisfying all these constraints always exists and there will always be a solution. Then in example 1, for n equal to 3, we want a sequence where 1 occurs once and rest of the numbers, that is 2 and 3, occurs twice. And one such sequence can be 2, 3, 2, 1, 3. Here 1 occurs once and 2 and 3 occurs twice, and the distance between the 2 is 2 and 3 is 3. But we have to return the lexicographically largest valid sequence, which is this one. And here also 1 occurs once and rest of the number occurs twice, and the distance between the 3's is 3 and 2's is 2. So this will be our answer. Similarly, in example 2, for n equal to 5, we can have a lexicographically largest sequence where 1 occurs once and rest of the numbers occur twice, and distance between the numbers, say I, is I itself. For example, distance between 5 is 5, 3 is 3, and so on. And that's why this will be our answer. And also in terms of constraints, n can be between 1 and 20. Now let's jump into the solution space. Now the problem asks for constructing a sequence meeting the described three major conditions, and we must also make it lexicographically largest. To represent the sequence, we can use an array with a fixed size, and the size of the array can be 2 into n minus 1 because the integer 1 appears only once and all the remaining integers from 2 to n, that is n minus 1 integers, appear twice. Hence, the total size of the result sequence will be 2 into n minus 1. So for example, for n equal to 3, we will have three numbers 1, 2 and 3 occupying 5 slots. So now number 2 and 3 can appear twice, but number 1 will appear only once. And now since the constraint mentions that we only have 20 elements, this hints at a high complexity solution. Here, because we need to explore all possible placements of the numbers while adhering to the constraints, backtracking becomes a natural fit. This is analogous to the n queens problem, where we try to place the queens on the board, and here we are trying to place the numbers in the sequence. The main idea is that we try to place the numbers in the sequence, and if a placement fails to meet the condition, we backtrack, undo the placement, and try the alternative positions. And now let's see how we can place the numbers. Now, one way is that we place the numbers, generate the valid sequence, and check if it is a lexicographically largest sequence. And this is a valid brute force approach, but with a very high complexity. But given the constraints, should we really do that? Since we want the largest sequence, we should try to maximize the sequence. So we must be greedy and prioritize placing the larger numbers first. For example, if n is equal to 3, we process the numbers in a descending order. So first we try to place 3, then we try to place 2, then we try to place 1, and so on. So to achieve this, we place the largest number n first to maximize the sequence lexicographically, and then place n minus 1, n minus 2 and continue until 1. And we can represent the current position using the variable say pause or index. And now when we place the numbers in the range 2 to n, we don't place the number once but twice. because they occur two times, and the two placements should be one at index pos and another one at index pos plus num, ensuring that the distance between them is exactly num. For example, we begin at position 0 and the largest number we have to place is 3. So if we place 3 at index 0, we don't just place 3 once, we place it twice, one at position 0, and then the second occurrence must be at index position plus 3, that is index 3. This accounts for the key rule where the distance between the two occurrences of integers I from 2 to n must be exactly I, and the fixed size of sequence 2 into n minus 1 ensures that there is enough space to satisfy these conditions for all the numbers. So once we have placed 3 successfully, we move to the next element, that is 2, which we can place at next available position, that is 1. And again we have to place 2 twice, one at index 1 and another one at index 1 plus 2, that is 3. But the index 3 is already occupied by number 3, and hence there is a conflict or an overlap. So one of the constraints is now violated. In such cases, we must backtrack, undo the placement of the last number and try the next number. Here it is 1, and we can easily place 1 here because for 1 we have to place only one number and this position is empty, so there was no conflict. But now the question is, how can we perform this backtracking operation? How can I know which numbers are placed already and which are not? For example, here 3 and 1 are placed now, but 2 is not. And this is where we can use the visited set to keep track of numbers that are already placed or used. And here, since the numbers are consecutive from 1 to n, we can use a Boolean array. Let's call it used, where the indices in the array corresponds to the number. This would act like a visited set. So for 1 and 3, we can mark true because they are already visited, but 2 is not. And now whenever we backtrack, we first mark the number as not used in the used array, and we clear the indices in the answer sequence that were occupied by the number. This ensures that we can try placing the same number again in a new configuration or place another number instead. Now continuing with our example, we have placed number 3 at position 0 and 3. Next we place number 2 at positions 1 and 3, but it caused a conflict. So we backtracked and tried placing number 1 at position 1, and that worked. And now only number we have to place is 2, that we can see from the visited set. So we try to place 2 at index 2 and 4, and this time the placement works successfully. And now this is the terminal case because we have processed all the indices of the sequence, that is position pos has reached at the end of the answer sequence. And at this point we check if all the numbers have been placed by scanning the used array. If any of the numbers is not marked as used, it means we cannot form a valid sequence and we can return false. However, the problem guarantees that the solution always exists, right? This case will not arise. Otherwise, we will return true, signaling that a valid sequence has been successfully constructed. Now, the time complexity of this approach is O of n factorial in the extreme worst case, as we might explore all possible placements of the numbers recursively. However, this is significantly optimized by greedily placing the larger numbers first to ensure that the sequence is lexicographically larger, and then we backtrack whenever we don't meet the constraints, hence pruning the recursion tree, making our solution efficient. And in terms of space complexity, it will be O of n, coming mainly from the recursion stack, representing the depth of backtracking when placing all the numbers in the sequence. Now let's jump into the code part. First, let's calculate the size of our answer, which will be 2 into n minus 1. Now let's initialize our answer array of this size and also create the Boolean array used of size n plus 1 to track the numbers that have been placed, and start the backtracking process with the helper method place numbers, which will take the number n along with answer and used array and starts filling in the answer array with position 0. And once the function completes, we will return our answer because the problem guarantees that there is always a solution. Now the function placeholders requires several arguments such as n, answer and used when its primary focus is handling the current position. So to simplify this, we can encapsulate the variables by moving them to the class level properties and initialize it inside the caller method. By doing this, we need to only pass the current position to this method, making the code cleaner and easier to manage. Now let's define the place numbers function. First, let's write the base case. That is, we check if all the positions are filled. If they are, then we will check if all the numbers from 1 to n are used by scanning the used array. If not, then we will return false. Otherwise, we will return true because the sequence is valid. Now the next thing we will check is if the current position is already filled. If it is, then we will try to fill in the next position. But if the position is empty, then we can fill it by iterating on the numbers starting from n down to 1 for the lexicographical order. And if the number is not used yet, then we check if number is 1. If it is, then it's a special case because we have to fill it only once. So we fill that number, mark the number as used, and recursively try to fill in the rest of the positions. If we can, then we will return true. Otherwise, we will backtrack by resetting the placement and marking the number as unused. Otherwise, if the number is not 1, then we have to place it twice. But before doing the placement, we can do a bit of pruning. That is, we eliminate the branches of search tree that cannot lead to a solution. We can only place the two numbers if the position of the second occurrence, that is position plus number, or the distance position is less than the length of the sequence and both the positions are not yet filled, that is the values at those positions are 0. So if both the conditions are satisfied, then we place a number at the current position and the distance position, mark it as used, and recursively try to fill in the rest of the positions. If we can, then we will return true. But if we can't, then we backtrack, undo the placement and mark the number as unused. And in the end, if we can't find any valid positions, then we will return false. Now let's submit this code. Awesome. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.